All right, we are live. Hello, hi, good evening, everybody. How are you guys doing today? So, here I am, and I welcome you to this marathon session for Term 2 exam. Now, I know your exams are tomorrow, right? So, what are we doing today? We are doing a very quick last minute revision so that the important concept and the important questions are completely thorough in your mind, right? Are you guys excited? Tell me. I can see a lot of comments here. Niranjana, hello, good afternoon. Square Films, time to do it. All interesting names that you guys have. Mohammed, hello, good afternoon. Chavi, hello, Niriksha. Hi, Sham. Hello, Puneet. Good afternoon, Beatrice. Good evening. Hello. Hello, Aaron. Hi, Manjeet. Hi, Varsha. Hi, Puneet. All right, there are so many people, so fast the comments are coming that I am not able to read them all very quickly. But yeah, I can see your energy. I can see how excited you guys are to attend this session. So guys, let's get started. All right. Now I know one day before the exam, right? A lot of you might be feeling a bit nervous. A lot of you might be feeling, oh my God, maybe I don't know a lot. Don't worry. What we have in this session is a complete and thorough revision, very quick revision, and we'll be solving questions that have been provided from the board in mock paper, right? So the questions that have been provided from CBSE in the mock paper. Let's get started. Okay. Poonam, hello. Mrityunjay, hello. Aaron, Joes, I can see. All right. Teddy Bear. Again, very interesting names. Hello, Pooja. Hello, Madan. Desi Chora. Hello. Hello, Piyush. Good evening. Divyani. Good evening. Poonam. Good evening. All right. They're just going very quickly. Namrata. Hello. Okay. Sanjeev. Hello. Hello, Vartika. Good afternoon. Hello, Aditi. Hello, Mrityunjay. Hello, Neha. Namrata. Mohammed Mishal. Pooja Sehgal, Kalyani, good evening, Jahanvi, Sanjay. All right. So, now that our chit chat is done, we'll be having this chit chat anyway throughout the session, right? Make sure if you have any doubts whatsoever, if there's anything that you do not understand, do ask in the chat window, all right? We'll keep on clearing doubts. We'll keep on moving forward. We have to make sure that no doubt is left unturned. All right, no doubt is left unsolved. All right, let's move on now. All in one is saying, ma'am, I'm facing problems with questions. Okay, no problem. I'll tell you how to attempt questions, and we are going to do them with marking scheme as well in today's session. Okay, let's get started. So, complete term 2 physics marathon, right? And guys, I know you have study groups, you have friends, so make sure you invite your friends to this session as well so that all of you can take advantage of the last minute revision and go crack the exam tomorrow, right? Okay, let's get started. In this particular session, we will be dealing with two major chapters, which will be current electricity and magnetism, right? Let's get started with current electricity first. So, in current electricity, we'll be dealing with certain concepts. Let's go to the first one, which is Ohm's law, right? Now, what is Ohm's law? What does it talk about? See, the idea here is that there are materials, some of them conduct electricity, they are called conductors. Some of them do not conduct electricity, they are called insulators, right? You know this already. If I take a conductor and attach the ends of a conductor to the two ends of a battery, that means I am providing potential difference to a conductor. Then current starts flowing through the conductor, right? You understand this? Now, if I take this potential difference provided to the conductor and map it with the current that is flowing through the conductor, that means if I take the voltmeters reading and ammeters reading and plot a graph, then at a particular temperature, this graph comes out to be approximately a straight line, and this is what Ohm's law says. At constant temperature, potential difference applied across the ends of a conductor is directly proportional to the current in the conductor, right? Now, this proportionality is Ohm's law, and the equality comes when we attach a constant of proportionality, right? So the constant of proportionality for this here is R. R is called resistance of that particular conductor, right? So you can understand that if there is a conducting material, right, it conducts electricity, but no material is perfectly conducting, right? It will have some opposition to conductance, right? It will have some opposition to conducting electricity. That is what is called resistance of that conductor, right? Now, SI unit of resistance is ohm, and here you can see that in this VI graph, slope of the VI graph is the resistance, all right? Now, the next concept here is, how does a resistance depend on the dimensions of a conductor, right? Say I have this conductor over here and it has smaller length. Here I've got a conductor, it has a larger length. Here I've got a conductor, it has a more cross section, right? What happens exactly? Which conductor will have more resistance? Which conductor will have less resistance? Now, the idea here is that you understand conduction happens because of flow of electrons, right? Flow of free electrons inside a conductor gives you electricity. Now, these free electrons, when they're flowing, right, just like traffic on a road, think about it like that, right? On a road, if you have a narrow road, you'll have more traffic, you'll feel more resistance. If you have a broader road, you'll have less traffic, right? Similarly, if you have a longer road, that resistance will happen for a longer duration. So here as well, if we take that analogy of traffic in a road, we can say that resistance of a conductor depends on its dimensions. It is proportional to, directly proportional to length of the conductor, inversely proportional to the cross-sectional area of the conductor. Cross-sectional area, the broader the conductor, more it will be able to conduct, less resistance. All right? Okay, all right. Now, here as well, there is a proportionality, as you can see, and R is proportional to L by A. L is length, A is cross-sectional area. This constant of proportionality over here is rho, resistivity. Now in here I can see, all right, Shikha is asking, ma'am, facing problem in electric power questions. Don't worry, Shikha, we will cover all of it in here in today's session, okay? Just have a little patience. We are covering electric power questions also. We are covering electric bill questions also, all right? Okay, okay. So, yes, we have magnetic effects as well. Amen is asking for magnetic effects of current. We have that as well in this session, okay? All right. Now, let's see what's happening here. We have resistance directly proportional to length, inversely proportional to area of cross section, and the proportionality constant here is called resistivity, right? Now, resistivity only depends on the material. If it's iron, it will have a certain value of resistivity at certain temperature. No matter you take a big block of iron or a small block of iron, doesn't matter, right? Similarly, copper, it will have a particular resistivity at, say, room temperature. If you take a bigger block of iron or a smaller block of iron, smaller block of copper, it doesn't matter, right? Resistivity only depends on material. All right, material and temperature. Now, let's talk more about this. All right, so as you can understand, resistance unit is ohm. So resistivity's unit is ohm meter. All right, from here only you can understand that resistivity's unit will come out to be ohm meter. Okay, now let's see. We have studied this much concepts. Let's go and solve a question. All right. So in board exams, as you understand, understanding a question is important. Understanding what is the concept behind the question to answer it is very important as well. But presentation of the answer is also very important, right? Because there are partial marks in the presentation. So let's go. Let's solve a few questions as well, right? Okay, now series combination of resistors. In series combination of resistors, a lot of the times, right, for equivalent resistance, you should know how to calculate equivalent resistance, right? So here I can say that if there are resistors that are attached such that their endpoints, right, their endpoints are attached such that there is no branching off in the wires, right? Here, as you can see in this circuit, the resistors are attached such that there is no branching off. Whatever current is going through, as you can see over here, current comes out of the positive terminal of the battery, it goes through the first resistance. Whatever current goes through the first resistance, the same current goes through the second resistance, same current goes through the third resistance, right? There is no branching off happening like this. This tells you that these are in series combination, and now I can say that if R1 has a potential difference V1 across it, R2 has a potential difference V2 across it, and R3 has a potential difference V3 across it, then these three potential difference adding together will give you the total potential difference that has been applied across the ends, right? That has been applied through the battery. Same current flows through each of the resistors, and from here we can say that, see, V1 plus V2 plus V3 is equal to V, and V1 is basically I times R1, so I times R1 plus I times R2 plus I times R3 is equal to I times R equivalent. From here, if I cancel out all of these I, then I get R equivalent is equal to R1 plus R2 plus R3, right? Now, once we calculate R1 plus R2 plus R3, do you understand that the current through this circuit can be calculated by equivalent resistance, and we can say that current is equal to I is equal to, let me write capital I is equal to V divided by R equivalent, total resistance. All right. Okay. Now here I have three resistors only. If I have n such resistors, then also the same thing happens, right? There you will say R1 plus R2 plus R3 plus R4 and so on till n, right? Okay. All in one is asking, when I'm saying question, when come in form, length is double, area is halved, what happens? Yes, those kind of questions also come, right? Proportionality based questions. Okay. Now, here we have understood series combination. Let's go to parallel combination, all right? And then we will solve questions based on resistors and circuits together, okay? So, now, what happens in parallel combination? See, in series combination, the same current flows through all the resistors, right? In parallel combinations, same potential difference is there through all the resistors. Here I have got these three resistors in parallel combination, right? That means the potential difference across the ends of R1 is equal to the potential difference across the ends of R2 and potential difference across the ends of R3. That's the idea. And the total current, it gets divided into branches. If I say the total current is I, it gets divided into three branches over here because we've got three resistors in parallel, I1, I2, I3, such that I1 plus I2 plus I3 is equal to I, right? Conservation of charge. All right. Aniket is asking, ma'am, what is 1 coulomb of charge? All right, 1 coulomb of charge is, well, 1 coulomb of charge when it's a unit of charge basically. All right, coulomb is a unit of charge. So 1 coulomb charge is, well, plus 1 coulomb charge. If you have a negative charge in 1 coulomb, you can say that, all right, negative charge in 1 coulomb. Okay? All right. Now you can calculate 1 coulomb charge in terms of the number of electrons required to get that charge. All right, that can be calculated always. Okay. Now here, let's come back to resistors and see. Equivalent resistance in case of parallel combination comes out to be 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3, and here it is in case of 3 resistors only, right? So if there are n resistors, we do the same thing. We say that 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3 and so on and so forth till 1 upon Rn. Alright? Okay, alright. Okay. Now, how to get that by which formulae? Alright, Aniket is asking which formulae. Beta Aniket, what you can do over here is you can remember the equivalent resistance formulae over here and the derivation of it, right? How do we get this result? We get this result by the conservation of charge principle, right? So here, as I've told you, I1 plus I2 plus I3 is actually total current I, and here itself I can say that I1 is current across R1, right? R1 resistor, this can be written as V by R1, right? Plus I2 can be written as V by R2 plus I3 can be written as V by R3. Now the thing is, in parallel combination, by definition, the potential drop across all the resistors is the same, V, right? So that's what I've written, and this is equal to V by R equivalent. Why R equivalent? Because if I take all of these resistors and replace them with a single resistor, then I should get the same equivalent current, right? That's what equivalent resistance is. So here if I cancel out these V, I get the same result. Alright? The same result that comes out equal to 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Okay? Alright. Now, for n number of resistors, we can say that 1 upon Rn, you will go till 1 upon Rn, and here's a shortcut, right? If I have got identical resistors, right? If I have got same value resistors, say for example 100 ohm resistors are there, and I have taken n 100 ohm resistors and connected them in parallel, then I can say that the equivalent resistance will be resistance of each resistor divided by n. Alright? It will come with simple calculations. Alright? Now, let's go and solve this question, guys. We have understood what series and parallel combinations are. We have understood how resistance varies with length and cross-sectional area of the conductor, how resistance varies with temperature, right? For a conductor, if you increase the temperature, resistance increases. If you decrease the temperature, resistance decreases. Now, here we've got a question. Let's solve this. This is given to be a 3-mark question, right? And the question is, the circuit is given to us. Calculate the total resistance of the circuit and find the total current in the circuit. 2 things we have to calculate over here, right? So, come on guys, quickly tell me in the chat window, what is the answer that you are getting? Okay, Kashif says 12 ohm and 12 ampere. 2 amperes. Alright, 12 ohms and 2 amperes. That's the answer that you are getting. Okay, alright. Aniket says 12 ohm. Ananya says 12 ohm. Alright. I can see most of you can get the answers very quickly, right? Now, what we need to do over here is to understand how to write the answer in the exam as well, right? Because presentation matters in board exams, not just calculating the answers, right? So, here we go. You can see that these 6 ohm and 4 ohm are in series, right? And then this entirety is in parallel with 10 ohm resistance, which in turn, this entire system is in series with 7 ohm, right? So here we can see that after applying series parallel, we can solve this question. So let's solve the question step by step, okay? Let's go to step 1. First thing what you do is start by reducing the circuit, all right? Start by solving the circuit. What do? We say that this is the circuit that's given. This can be written as 6 ohm and 4 ohm are in series. In series, we add the resistances. So what becomes? 6 plus 4, 10 ohm, right? So here we go. This 10 ohm remains as it is, but this 10 ohm is a series combination of 6 and 4, right? Now, what we have is these 10 ohm and 10 ohm, they are in parallel, right? And when you solve the question mark step by step, right, you will get partial marking. That is very important because at the end of it, right, maybe you make some calculation error. If you solve the question step by step, you will get marks for the steps. even if you make some error in the end. Okay, so be safe that way. Now here you can see that after this what happens, we've got 10 and 10 parallel, that gives me 5 ohm, resultant of 10 and 10, and then here I've got 5 ohm and 7 ohm in series. 5 ohm and 7 ohm in series will give me, yes, 7 plus 5, 12 ohm, right? Okay, so here you can see that 12 ohm is the net resistance and battery is of 24 volt, right? So the potential difference applied across the circuit is 24 volt. Total current comes out to be how much? 24 divided by 12, right? So with partial marking, here I've got 12 ohm as one part of the answer. The next part of the answer is, yes, 12 volt divided by 12, 24 volt divided by 12 ohm gives me 2 ampere. Is that fine? Current is equal to V by R. Okay, all right. Beatrice is asking, ma'am, how to identify if they are in parallel? Okay, one very easy way to identify if they are in parallel, if both their endpoints are joined, right? So here as well, do you see? I'll go to the previous page, okay, and I'll tell you. Here, can you see that? If I have this R2 and R5, these two resistors, right, they are in parallel. How do I know that? Because their endpoints are joined. R2's endpoints, X and Y, and R5's endpoints, X dash and Y dash. Do you see that? They are joined, right? Joined by a simple connecting wire. There's no element in between. That is how we know they are in parallel, all right? Potential difference across these two resistors are going to be the same. Okay, all right. Now, let's move on. Why is field inside the magnet straight? Okay, all right. We'll come to magnetic field lines and field inside a magnet, okay? Let's move on now. The next thing that we have in current electricity is heating effects of current, all right? So, as I've told you before, free electrons, they are the ones that make it possible for a conductor to conduct, right? Free electrons are the ones that flow. So, here what happens is, as the free electrons flow, they collide with each other, and as they collide with the lattice of the conductor, they generate heat, right? That's what happens. And that is why the more the resistance, the higher the energy produced, all right? The higher the energy generated. So heat dissipated by a resistor, there's a simple formula here that you can see. Heat generated by a resistor is equal to I square R into T, all right? I square is square of the current inside the resistor. So if there is a resistor, R is a resistance, I is the current given to it, then I square R into T. T is the time for which that current is given, right? If this is given, then this is the heat generated by the resistor. Now, this heat, as usual, I mean, if it's any kind of energy, right, its unit is going to be joule. So that's what the SI unit here is. And if I take this I square R into T, right, this relation, and use Ohm's law to actually manipulate it a little bit, right? Because I know that I is equal to V by R. This we have already, right? Now, what we can do is, we can manipulate the given relation I square R into T in terms of I and R. We can get the relation in terms of V and R. We can get the relation in terms of I and V as well, right? Why? So that if I know only resistance and potential difference, I would be able to apply. If I know only current and resistance, I would be able to apply that relation and get the answer. All right? So here you can see that H is equal to V into I into T as well. It's equal to I square R into T as well. It's equal to V square by R into T as well. Okay? No problem till here, right? No confusion whatsoever. Okay, all right. Now that we understand the basic concept and the formulas that are relevant, let's go solve questions. Okay? Disha Bhatt is asking, what is lattice? Please tell. All right, Disha. So the idea here is that lattice structure of any conductor, any material is basically the structure in which the atoms are arranged. All right. You will study more about lattice in physics as well as chemistry, all right, in 11th and 12th grades. Right now, just understand that a solid is a solid because it has a structure in which the atoms are placed. Okay, that is what I was talking about. Okay, what is Joule's law of heating? All right, I think we have covered this already here, right? Okay, come on guys, quickly. Let's solve this question and let's see how to represent the answer in the board exams, right? This is a 2 marks question, right? It was there in the mock paper provided by the CBSE. So let's see. The question states, a student boils water in an electric kettle for 20 minutes. Using the same main supply, he wants to reduce the boiling time of water. To do so, should he increase or decrease the length of the heating element? Justify your answer. Should he increase the length, decrease the length? Come on guys. Aditi says decrease the length. All right. Kashif says increase the length. I can see a lot of answers. A lot of you are saying increase, a lot of you are saying decrease. But what's exactly happening? What's the logic behind it? Right? That's what we have to understand. So, looking at the logic, see, I want to look at the basically, what is the student doing? He's boiling water, right, for 20 minutes. So, can I say that heat that we get will be equal to V square by R multiplied by T, right? V square by R into T. T is the time for which he is boiling water, right? This is the heat. Now, do you understand that? Here they're saying using the same main supply, he wants to reduce the boiling time of water. Basically, he's taking the same amount of water. He wants to boil the same amount of water. That means the same amount of net heat is required, right? The same amount of total heat is required. This is constant. He wants to reduce one multiplier, right? He wants to reduce time. So what should he do? Increase the other multiplier, right? He should be increasing the other multiplier. Right? That means this value of V square by R should be increased. But he wants to use the same main supply. What does that mean? It means that the potential difference that he is applying is still the same. Right? So the potential difference he is applying, he can't vary that. So what to do then? If you want to increase the entire value, the denominator should be decreased, right? Exactly. So you want to reduce the resistor. All right. To reduce the resistor, what should we do with length? Come on guys. How do we reduce the resistance? Yes. Reduce the length, resistance reduces. Right? Exactly. So reduce the length. That's it. And how do you write this explanation? You can say that here H is V square by R into T. We are talking about reducing the boiling time using the same main supply, right? The rate of heat production should be large. Voltage is constant since we are using the same main supply, right? Same electricity supply you're using. Voltage is constant, resistance should be decreased. Resistance will be decreased only if length is decreased, right? Because R is proportional to L by A. Cross-sectional area is not even mentioned in the question. They're asking only about length of the conductor. So, to reduce the resistance, length should be reduced. Okay? Alright, alright. Decrease the length of the heating element as surface of the, okay. Correct, alright. Let's move on now. Here we go. Let's go to electric power, alright. So we've understood heating effect, right? We've understood the energy that is released, the heat that is released by a resistor. Let's go and understand power now, right? What is power? For any kind of energy production, right? What is power? Rate of energy produced. Okay? All right. So if I have energy being produced as, well, I can say that energy being produced is what? I square R into T. Now, the rate of energy being produced with respect to time, rate of change of energy being produced with respect to time, that will be just energy divided by time. This gets cancelled out. I am left with I square R, right? So similarly, I can say that the other forms of this relation will be I square R, VI, V square by R. Okay? This is what power is. When do we use P equal to VI? Aditi is asking. Alright. So the thing is, when you have potential difference and current, but you don't know resistor, right? Then you can use power equal to VI. Instead of calculating resistor and then substituting in another format, I square R or V square by R, what we do is we directly substitute it in this format, VI. That's all. Okay? So these three formats are there only for our convenience, depending on what value, what quantity is given in the question to solve the question. That's all. Alright? Okay. Ananya is asking, ma'am, why not I square RT in the previous question? Again, the same idea. See, I could have written energy as I square RT, VIT or V square by RT, right? But there we were talking about potential difference was given as constant and we were talking about resistance, right? Current was not even being discussed anywhere. So the condition given was that potential difference is constant. And so if I utilize a formula in which potential difference is there, then I can use that, right, in solving the question. That's what we did. I hope you understand this, right? All right. Let's go. Let's understand more. As I told you, these are the three formats that we have. P equal to VI, P equal to I square R, P equal to V square by R. Depending on what is given in the question, we will use that formula. Okay? That's all. This is for our convenience. All right. Mohammed Afzal is asking, ma'am, please teach problem sums. Yes, let's go. Let's solve questions as well. We are going to solve questions as well. All right. Okay. Now here is a very quick analogy between the relations of power and relations of energy. As you can see, in here VIT, if I divide it by time, I get power V into I. Here as well, from heat, I square RT, if I divide it by time, I get power I square R. Here as well, V square by R into T, if I divide it by time, we get power V square by R. Effectively, heat generated divided by time is going to give me power. And this is average power generated. Alright? Okay, alright. Okay, how to know what? Okay, why is ammeter likely to be burnt when connected in parallel? Yeah, Rehab. The thing is, ammeter, through an ammeter, when you're constructing an ammeter, right, you construct an ammeter using a galvanometer. And a galvanometer is a very, very sensitive instrument. The current that a galvanometer uses for deflection is in milliamperes. Alright. And that is why when you create an ammeter, right, you want to make sure a very small amount goes through the galvanometer. Now, as far as connection of ammeter in the system, right? So, if you want to measure current in this particular branch, then you have to connect the ammeter in this particular branch itself, right? So that the current that is going through the branch goes through the ammeter and you are able to detect the reading. That is why ammeter is connected in series, okay? Not in parallel. If you connect an ammeter in parallel, it will not give you the reading that you want in the first place, all right? And as far as being burnt out is concerned, in any ammeter, it has its, well, largest current that it can handle because of its construction. All right? Okay. Let's move on, guys. Let's talk more about electric power. Now, I know you guys are familiar with this figure, right? This is there in all our homes. Come on, we use electricity in our home, right? And when we use electricity in our home, we buy this electricity at a certain rate, right? So this meter, electric meter, is there in all our homes. This calculates how many units of electricity we've consumed. Based on this calculation, every month we get electricity bill and we have to pay up. Otherwise, electricity is cut off, right? Exactly. So how does this meter measure electricity, or rather in what unit does it measure electricity? Consumption, right? So what it measures is consumption of electricity, and that is measured in kilowatt hour. All right. So basically think about it like this. Consumption of electricity, what are we consuming? We're consuming electric energy, right? Yes. So this is measuring consumption of electrical energy. And energy is going to be power into time, right? That's what it is. So kilowatt, what is unit of power? Kilo is just 1,000. So kilowatt is 1,000 watt, right? Into time. Instead of measuring it in seconds, because second is a very small quantity, right? Here it is measured in hours, so that it's a manageable number. All right. So here we have 1 kilowatt hour is 1 unit of energy that's being consumed, and this consumption is being measured as 1000 watt into 3600 seconds. There are 3600 seconds in 1 hour, right? 60 into 60. So here we go. 3.6 into 10 raised to power 6 joules is the energy that's being consumed when 1 unit of electric power is being consumed, 1 kilowatt hour. All right. Okay, all right. Ma'am, what is the keyword in identifying the formula whether power or heat? The keyword is, it will always be there in the question. If you have to calculate power, then you have to calculate power and then you will apply V square by R or I square R or VI. If you have to calculate heat generated or energy consumed, right, then you have to apply the energy heat formulas. Okay? All right. Let's solve a question and see. Okay, so this is again one of the questions that was there in the mock tests. As you can see, it's a 1 mark question. Let's see, it would cost a man rupees 3.5 to buy 1 kilowatt hour of electrical energy from the main electric board. Now, do you see that? 1 kilowatt hour of electrical energy they're talking about, right? So they're talking about energy here. You see that? Okay, his generator has a maximum power of 2 kilowatt. Power 2 kilowatt. See, it's given in the question. Now, the generator produces energy at this maximum power for 3 hours, right? The generator is producing electricity at this particular power for 3 hours. Time is given here as well. Power into time is energy. So, calculate how much it would cost to buy the same amount of energy from the main electricity board. What are they talking about? They're talking about how much would it cost to buy the same amount of energy. That means we're equating energy, same amount of energy from the main electricity board, right? You understood the question? How to apply it? We have to basically equate energy from one source and from the other source. Here we go. Let's equate energy. All right? So, as you can see, energy is power into time, right? So, when we calculate energy consumed, right, we can say that the generator is giving a power of 2 kilowatt and the generator is being used for 3 hours. 2 kilowatt into 3 hours gives you 6 kilowatt hour. This is the energy. Energy that's being consumed from the generator. Now we want the same energy to be bought from the main electrical board. What do? We equate the amount of energy. We will say that cost of 1 kilowatt of energy is given as 3.5 rupees. So cost of 6 kilowatt of energy will be how much? Cost of 6 kilowatt of energy will be 21 rupees. 6 into 3.5. Understood? All right, all right. So, do you understand the difference between using power formulae and using energy formulae? I hope you did. All right. Let's move on now. This was electricity, very quick revision of concepts, and we solved a few problems as well. Let's go to magnetism, and here as well, let's go to the major concepts first. So, the first thing about magnetism we are going to be revising is magnetic field lines. Now you understand that electromagnetism as a whole, right? There's a whole electromagnetic field. There is no separate electric field and separate magnetic field. What we do is, rather, we understand, we learn them separately so that we can understand the entire thing together. Okay? Alright, so one part we understand electric field, on the other part we understand about magnetic field. Both of them, on the other hand, are to do with charges. Okay? Both of them get generated by charges. So, when we talk about electric field gets generated due to static charges, right? Charges that are stationary. You will study in 12th grade electrostatics, an entire chapter based on this. For magnetic field, they are generated by moving charges. Alright, in fact, when we talk about a magnet, right, or a magnetic material, ferromagnet or a magnetic materials also get their magnetic properties because of moving charges. Electrons, there is a spin of electrons. Alright, I won't go into detail, but do understand that magnetic field is generated only by moving charges. Alright, okay. Now, here I've got this magnet. It actually produces magnetic field, but we're not able to see it, right? So what we do is, we understand the graphical representation, right? We make these lines so that we can understand the variation of magnetic field, and that is what magnetic field lines are. Okay? Alright, alright. Now, what are the properties of magnetic field lines? Although we make magnetic field lines in order to understand magnetic field better, there are certain properties of magnetic field lines that will always be true. Alright? So, first things first, magnetic field lines due to a magnet will always be from north to south pole outside the magnet and from south to north pole inside the magnet. Alright? Then, magnetic field lines form continuous closed curves. It's going to be there always. Okay, magnetic field lines form continuous closed curves. Degree of closeness of field lines determines the strength of magnetic field. If magnetic fields are very close together, too many magnetic field lines closer together, that tells you it's higher value of magnetic field in that region. If the magnetic fields are sparse, far away from each other, then that tells you that there is less amount of magnetic field in that region. Alright? No two field lines intersect each other, right? That's important. Field lines are never going to intersect. Why? Because the tangent to a field line gives you the direction, right? So if you draw a tangent over here, it gives you direction of magnetic field. If you draw a tangent here, it gives you direction of magnetic field at this point, right? So now, if magnetic field lines intersect, that means we don't have a unique direction. That's not possible. Alright? So, here we go. No two field lines are going to intersect each other, never going to intersect. Alright? They are imaginary lines. Magnetic field lines are imaginary lines. We are drawing these lines so that we can understand the variation of magnetic field better. Alright? Yes. Let's move on. Here we go. Let's understand what are the different ways in which magnetic field can be produced. Right? So here we've got straight current carrying conductor. It is going to produce magnetic field because current is carried inside a conductor due to moving electrons, right? Moving charges will always give you magnetic field. So here we go. Straight current carrying conductor can produce magnetic field, and we can understand how. See, this is how the magnetic field lines come about. If I have a straight current carrying conductor and I want to plot the magnetic field lines, I'll say that the magnetic field lines will always form closed loops, and the direction of magnetic field lines can be calculated, can be understood from right hand thumb rule, alright, or right hand curl rule also we call it. What? You can always place your thumb along the direction of current, and as you curl your fingers, you get the direction of magnetic field lines. Okay? So here, as you can see, if the current is going up, this is how magnetic field lines will be. If the current is going down, this is how magnetic field lines will be. Okay? Alright. Now here also, you can see that magnetic field strength, the strength of magnetic field at Q is greater than at P, because at Q, the magnetic field lines are closer together. At P, they are farther away. And as you can see, the magnetic field strength increases with the current. Since this magnetic field is produced because of a current, if I increase the current, magnetic field will increase. Obviously, right? And if I reduce the current, magnetic field due to this current will reduce. B is directly proportional to current in the conductor. Alright? Okay. Now, let's move on. I hope you've understood this basic concept here, right? Right hand thumb rule, as I have told you, right? The direction of magnetic field lines can be calculated by right hand thumb rule or right hand curl rule as well. If you place your thumb along the direction of current, the curl of your fingers gives you the direction of magnetic field. Okay? Let's move on now. If I have a current carrying circular coil, then what happens, right? A current carrying circular coil, magnetic field due to a current carrying circular coil looks very similar to magnetic field generated by a magnet. Alright, so if I have, instead of this current carrying circular coil, if I place a magnet here as well, north here, south here, it's going to give me the same kind of magnetic field lines. Alright? Okay, alright. Here as well, you can understand that since this magnetic field is produced because of the current, as current increases, magnetic field strength will increase. As current reduces, magnetic field strength will reduce. If I make the current zero, magnetic field becomes zero. Okay? Here I've got a question. Charvi says, when a conductor is moved relative to a magnet, magnetic field associated with the changes, current is induced. Yeah, that's electromagnetic induction. Guys, we are going to come to that in a while. Okay. Here as well, you understand that the magnetic field lines are very similar to as if I've put a bar magnet here, and in a bar magnet also, I can say that if I look at it from the top, this N over here, right? If I look at it from N, this is the direction of current. This is the direction of current that I get. If I look at it from the south, this is the direction of current that I get. You can easily understand it from, well, the diagram over here, right? The way you write N and south, you'd be able to understand how the direction of current is to produce an effect equivalent to which kind of magnet, which orientation of magnet. All right? Okay. All right. Now, let's go to the next concept here. Current carrying solenoid. Now, what is a solenoid? A solenoid is just a coil, all right? A coil that is bound very tightly, pretty long coil where the number of turns are a lot and length of the solenoid is pretty big compared to the radius of the circles, radius of the coil, all right? That's all there is to it. Now, here I've got a current carrying solenoid. As you can see, here you can see that the magnetic field due to this solenoid, right? The butterfly kind of a shape of magnetic field lines, it's pretty similar to a bar magnet, but here magnetic field is generated because of the current in the wire. All right. So as you can see, magnetic field strength increases if I increase the current or if I increase the number of turns also, right? If I increase the number of turns. Now think about it that way. If I have one coil, it gives a certain amount of magnetic field. If I have two coils, it's going to give double amount of magnetic field. If I have three coils, it's going to give even more. If I have four coils, even more, and so on and so forth. If I keep increasing the number of loops, the magnetic field keeps on increasing. Okay? Now, here as well, you can see that the current in the solenoid is provided by a battery. I can replace the existing battery with a bigger battery, with a higher voltage battery, increase the amount of current and increase the amount of magnetic field generated over here as well. Okay? Guys, focus here on the session, all right? Okay, let's go. Let's move on. Here I've got a question. Okay? Question on solenoid. It's a 2-mark question. You can see the mark distribution in the solution as well. A circuit contains a battery, a variable resistor and a solenoid, right? That's what there is in the circuit. You can see that A variable resistor is there, R, this is a battery, voltage V, and this is a solenoid. The figure below shows the magnetic field pattern produced by the current in the solenoid, right? These are the magnetic field lines that are produced. Now the question starts. State how the magnetic field pattern indicates the regions where magnetic field is stronger. How do we understand where magnetic field is stronger? Come on. How do we understand where magnetic field is stronger? By the magnetic field lines, right? The closer together field lines will have higher magnetic field. Farther apart field lines will have lower magnetic field. Alright, Prerna is asking, you teach math also, right? Yeah, Prerna, I teach math as well. Alright, okay. So, what happens here? Where are magnetic field lines? More closer together, inside, right? Here, inside the solenoid. That's where the magnetic field is more. Okay, closeness of magnetic field lines indicates the strength of magnetic field. Since the field lines are crowded around the ends inside the solenoid, these are the regions with stronger magnetic field, right? Now, once you write the reason really well, you get the partial marks. What is the second part of the question? Second part is, what happens to the magnetic field when the current in the circuit is reversed? Yeah, what happens? What happens when the current is reversed? Well, from right hand thumb rule, I know that if my thumb is pointing up, the field lines are going to curl along the fingers. If my thumb points down, what happens? The field lines are going to curl in the opposite direction, right? That's what happens. So, what happens to magnetic field when the current is reversed? Magnetic field lines also get reversed, right? Direction of magnetic field will also be reversed. Alright, that's it for a solenoid. Let's get to another subtopic, okay? I hope till now you're understanding everything, right? If you have any doubts whatsoever, do ask in the chat window and I'll be sure to answer it, alright? Problem sum. Yes, Afzal, we are doing problem sums as well. You have had a Menti quiz and we are going to attach, solved problems as well, okay? You'll be able to find them in the description. Now, here we go. Force on a current carrying conductor due to a magnetic field. See, as I told you before, moving charges and magnetic field, they are very strongly related, right? If I've got moving charges and magnetic field, right? I can say that moving charges are going to create magnetic field and an existing magnetic field is going to apply force on moving charges. Okay, that's always going to happen. So earlier we understood how magnetic field is created by moving charges, right? When there is current inside a conductor, basically electrons are moving inside the conductor, right? So earlier we understood one part of it, magnetic field produced by moving charges. Now we are going to understand the second part of it. If there is an existing magnetic field, what force does it apply on moving charges, or rather a current carrying conductor? Okay, here we go. As you can see, the force that is applied on a moving charge, right? The force that is applied on the moving charge is dependent on the current in the current carrying wire, and here force is directly perpendicular to, in fact, here is Fleming's left hand rule. As you can see, direction of force, magnetic field and direction of current, all three are perpendicular to each other. Okay, force is I dl cross B. Basically, it is perpendicular to the magnetic field and it is perpendicular to the direction of current. Alright? You can use Fleming's left hand rule to figure out the directions. See, if I take my left hand, I'll say that direction of force is given by my thumb, the direction of magnetic field is given by my index finger, and the direction of current is given by the middle finger. Alright? Okay. Where is strength high inside the solenoid or end? Alright, Anushri Solanki is asking. Alright, Anushri, my name is Anushri as well. Okay, so the thing is, in solenoid, magnetic field is highest at the center. Okay, in a realistic solenoid. In your syllabus, you have only ideal solenoid, alright. But even if you go to a realistic solenoid, the magnetic field is highest at the center inside the solenoid, and as you go towards the end, magnetic field is going to reduce. Okay? All right. Can you repeat this again? Sujata Guransh is asking, what exactly do you want me to repeat? Okay. All right. Let's move on. And here, I hope you understand force, magnetic field, and current. These are mutually perpendicular. Right? This is what is the concept that you need to know here. All right? Okay. Let's move on now. Here, Gursharan. Good evening, Gursharan. Hello. If you have any questions, do ask. All right? So straight line shows higher magnetic field in solenoid. Actually, strength of magnetic field will be told to you by the density of magnetic field lines, right? Denser magnetic fields. And yes, coincidentally, in case of solenoid, at the center, you do have denser magnetic field. Actually, there is a whole mathematical calculation for magnetic field. Later in 12th grade, you will learn about it. All right? Not now. Okay. Electromagnetic induction. Let's come to electromagnetic induction. It's a very, very interesting chapter. In fact, later on when you study magnetism in detail, you will learn much more about electromagnetic induction. So what happens? Electromagnetic induction basically tells you if there is a loop, alright, if there is a conductor loop and through the loop, the magnetic field varies, right? If there is a conducting loop which is not carrying current, by the way, right now, if you vary the magnetic field lines through the loop, then it's going to start conducting current, right? That is what is electromagnetic induction. Okay, so here, as you can see, there are two cases. You can see this is a magnet. The magnet is moving towards the loop over here, right? This loop, right, this coil is not connected to a battery, right? There is only an ammeter here or a galvanometer here that's going to measure the deflection. The deflection is going to measure whether there is a current or not. All right. Now in here, do you see that as the magnet moves, whether it's moving towards or it's moving away, there is going to be a current that's going to be generated in this coil. If the magnet stays in its place, there is no movement, there's no relative motion between the magnet and the coil, then there is not going to be any electricity, there is not going to be any current induced. All right? How is electricity produced when conductor passes near the magnets? Yeah, the electricity is produced only when there is relative motion between the magnet and the coil. All right? If there is no relative motion, then there will not be any current induced. And induction of current happens, you will study that later. All right? You will study about magnetic flux. When magnetic flux changes, then only induction of current happens. All right? Let's understand more about it over here. You see that current is moved in magnetic field, or rather a conductor is placed in changing magnetic field. Effectively, we are talking about changing magnetic field, right? So, if I have a moving magnet, what does that tell me? If the magnet moves, then magnetic field at any given point is going to change, right? Because when the magnet was near it, it had a different value. When the magnet is away from it, it had a different value, right? So, the key word here is changing magnetic field. All right, whether you change that magnetic field by moving a magnet, or you change that magnetic field by electromagnet also, you change the current in an electromagnet and its magnetic field generated will change, right? Yes. So electromagnetic induction will happen always when a conductor is placed in a changing magnetic field. Okay. All right. Aftab says, why only a coil? Why not a cylinder or a cuboid? Beta, we need to close the circuit basically. All right. So their current is going to flow only when there is a closed circuit, right? Electromagnetic induction happens in a say cuboid conductor also. All right. But you will not be able to measure the current in the galvanometer. You will not be able to detect the current because there will not be any current. Current will come only when there is a closed circuit. That is why loop. Okay. All right. Now, Lakshita is saying electric motor. Yes, electric motor, for that there is a separate a detailed session that was done yesterday, all right? So link in the description for electric motor. Do watch that session in detail. Electric motor is a very important concept for tomorrow's exam, so do not miss it, okay? All right. Now, to understand the direction, here is Fleming's right hand rule. You can see that. If you place your thumb, okay, I'm going to say, here is how you place your fingers, right? If you place your thumb along the direction of motion, your index finger will give you the direction of magnetic field and your middle finger will give you direction of induced current, okay? All right. If the magnet is kept stationary without movement, will the magnetic field change? Yeah, Vijaya is asking a very good question here, guys. If the magnet is kept stationary, will there be any induced current in the coil? Now, look at my hands very carefully. I'm keeping the magnet straight. I'm keeping the magnet at its position. But I can move the coil towards the magnet also, right? Even if I keep the magnets as it is and I move the coil towards or away from the magnet, then also there is a relative motion between the magnet and the coil. There will be a change in magnetic field that the coil is passing through the coil, right? That's all. There will be induction. So one or the two can move. As long as there is a change in magnetic field, there will be induction. Okay? All right. Let's go. Let's understand this question. Yeah. Here we have Ansari sir was demonstrating an experiment in his class, which setup is shown in the figure below. Right. So we've got a physics teacher. He is showing an experiment. Here, as you can see, a magnet is attached to a spring. The spring can go in and out of the stationary coil. All right. The spring can go, the magnet can go in and out of the stationary coil because it is attached to a spring. Now, he lifted the magnet and released it to make it oscillate through the coil. Of course, if you just lift the magnet, release it, the magnet is going to oscillate because of the spring, right? Yes. Based on your understanding of the phenomenon, answer the following questions. Come on, guys. Let's try to understand this, right? First question is, what is the principle which Ansari sir is trying to demonstrate? Yes, the principle is electromagnetic induction, right? If you've got a moving magnet and a coil, then yes, there is going to be electromagnetic induction. Answer is electromagnetic induction. It's a one marker. Yeah? Okay, Shikha Jaiswal is asking, what is the difference between galvanometer and ammeter? Alright, beta, galvanometer and ammeter both detect and measure current. Alright, the only difference is the amount of current or the sensitivity. How sensitive those instruments are. Galvanometer is a very, very sensitive instrument. It can detect electricity, it can detect current in microamperes also. Right, micro is 10 raised to minus 6. Ammeter, on the other hand, is also used to measure current and detect current, and it is used to measure current in our regular circuits. So the current is measured in amperes or 0.1 ampere, 0.2 amperes, 2 amperes, 5 amperes, those range of current. Okay? The inside construction of galvanometer and ammeter is pretty different, and there you will study more about it when you go to 12th grade. Alright? Okay. Now, let's solve this question, yeah? So, second part of the question is, what will be the observed when the magnet starts oscillating through the coil? Explain the reason behind this observation. See, as the magnet starts oscillating, what happens? Current flows through the coil, right? When the magnet is coming down, one direction current. When the magnet is going up, another direction current. That's what happens here as well. The galvanometer deflects back and forth, right? If the current flows through the coil, what does the galvanometer do? It deflects, right? If the current is flowing in this direction, this is how galvanometer will deflect. If the current is flowing in the opposite direction, the galvanometer will deflect in the opposite direction, right? So galvanometer, as I told you, is used to deflect, is used to detect, figure out if current is flowing or not. Even if a very small amount of current flows, galvanometer will be able to detect it and tell you, yes, there is current. Okay? All right. Now, the third question is Consider the situation where the magnet goes in and out of the coil. State two changes which could be made to increase the deflection in the galvanometer. Right, here as well. You want to increase the deflection in the galvanometer, right? Increase deflection means increase current induced, right? Because more current, more deflection, right? Okay, so what can you do to increase the induced current? You can do two things, right? You can either make sure the speed of the magnet is higher, right? You can make sure the speed of the magnet is higher, or that means you can actually pull it or push it more when starting the oscillations. But if that is not possible, then you can use a stronger magnet, right? Stronger magnet will produce a stronger magnetic field, so the changing magnetic field will be stronger, and so electromagnetic induction will be stronger. Stronger current will be produced. Okay, you can use a stronger magnet, or you can use a coil with larger number of turns also, right? Okay, all right. And yes, see, increase the turn of the coil, increase the magnetic, use a stronger magnet, or you can take the magnet and move it with a larger speed. I hope this is clear to you, right? Very, very interesting chapter, very, very interesting concepts. Later on, when you study it in detail in physics, you will realize what I'm talking about. Let's go and understand more, right? So here, another part of the question. Is there any difference in the observations in galvanometer when the magnet swings in and out of the stationary coil? Justify your answer. Is there any difference in observations in the galvanometer? What are we observing in the galvanometer? We're observing deflection. We're observing how much is deflected. That tells you the amount of current generated, and direction of deflection. That tells you in which direction the current is generated, right? In which direction the current is induced. So here, what is the difference in observation when the magnet swings in and out? See, the direction of current changes. When the magnet moves into the coil, the galvanometer shows a momentarily deflection towards one side, right? If it's going in, deflection will be on one side. If it's going out, deflection will be on the opposite side, on the other side. So that's the observation over here, right? As you can see, this is due to increasing and decreasing magnetic field associated with the coil as the magnet moves in and out of the coil respectively. The induced current in the coil is in opposite directions. So you have to mention all of this, right? You have to mention the answer and you have to mention the reason as well. Here, as you can see, the partial marking. Okay? Ayushi is asking, will diagrams be asked? Yes, Ayushi, diagrams can very well be asked. In fact, as I told you, DC motors, right? Electric motors, do go through the video that was released yesterday and make sure you have the diagram at hand properly. Okay? Alright, when is induced current maximum? Induced current in this situation is going to be maximum when velocity is maximum. Okay? When speed of the magnet is going to be maximum, in this particular situation, that's when induced current is maximum. Alright. How to know which direction, north or south, galvanometer deflects? Right hand thumb rule. Alright. Right hand thumb rule. This entire PPT, this entire session will be available to you guys in the form of a PDF. Do make sure to download it, and in here as well you will see the answer to all your questions. Alright? Okay, okay. Now, with this, I will end this session, right? And if you have any doubts, any questions whatsoever, you can go through the library of videos that we have. We have all of it, all of the concepts explained here. Okay? Now, there will be a complete science Mega Menti final quiz at 7:30 p.m. Alright? So do make sure you attend that. And guys, all the best, all the very best for tomorrow's exam. Go there, be relaxed, be happy, solve the paper and come out happy. Happy learning. Bye-bye, guys. All right?